Alright guys, I got a couple examples here of systems. I'll go ahead and show you the examples first if you'd like to pause the video and try to work them yourself. So here's example 1. Here's example 2. Example 3. And finally, example 4. So feel free to pause the video and try to work each one of those yourself. And then come back and check and make sure that you did it correctly. So number 1 here, remember that when you're solving the system, there are kind of a couple of different ways you can do it. We talked about one method being that you can use substitution. You could also do elimination. Those are the two algebraic solutions. In some instances, you can actually solve by graphing and looking to see where the two equations would overlap or where they would intersect at. And then the last way, you could solve it using a matrix, but a matrix doesn't work as well for quadratics. I don't think so. At least I don't think I've ever used a matrix. So there may be a way to do it, but I'm not familiar with that method yet. So I'm going to show you the two algebraic solutions today, and then to show you what can happen when you're working these. So before we get started, let's actually talk about different types of things that can happen. So one thing that we could see when you're graphing quadratics is maybe you've got a quadratic that does something like this. Makes your typical parabola shape, and it has a vertex here. And maybe you've got another parabola that opens downward, such that they share the same vertex. So here we have a situation where we would have one solution. They would cross at the vertex, so that's one possibility. We could also have a situation show up where maybe our parabola does something like this, and then we've got another parabola that goes exactly where we're talking about. So basically we're graphing the same parabola twice. So this system would be called consistent and dependent, because it has infinitely many solutions. We're graphing the same two equations here. So you would write your solution set in interval notation and say that it's all the points such that y equals whatever your equation is of your quadratic. So all the points on the line. Okay, just to go back here, when you have one solution, or if you can count the number of solutions, you would classify that system as consistent and independent. Alright, so this goes for one solution or two solutions. That would be, if you can count the number of solutions you have, you're good. If you can't count them because there's infinitely many, then it's dependent. Okay, and then finally we could have a situation show up where one of our quadratics does something like this, and the other one maybe does something like this, and they don't cross at all, and that system would be called inconsistent, and the solution would be, well, there isn't one, so we'd write no solution. Okay, so those are your three types of systems that you can have show up. So let's look and see if we've got any of those here. So hopefully, I think I've made one of each, so, or perhaps, maybe not, I don't really remember. So, looking at this first one here, we're going to solve it using the substitution method. So notice that both of these equations are equal to y. So I can substitute in the second equation, this part in for y here, and get one big equation with no y's in it. So I have negative x squared plus 2x equals negative 2x squared plus 12x minus 16. I'm going to try to get everything on the same side here. So I would add x squared, and I would subtract the 2x, like so. And then I'm going to divide everything by a negative 1 because it's difficult to try to factor when your leading coefficient isn't positive. At least for me it is. So x squared minus 10x plus 16, which will now factor as x minus 8 and x minus 2. And then the zero product rule says that if you've got two things that are multiplied together and they equal 0, then one of those things has to be 0. So we're going to set them both equal to 0 and solve for x. So we get that x equals 8 and x equals 2. So we have two different solutions here, and I need to solve for y in both cases. So I'm going to take what x is equal to and plug it back in to our top equation and see if I can solve and find the y values. So here y would equal negative 48, and here y would equal 0. So my two solutions, one of them lies at the point 8, negative 48, and the other one lies at the point 2, 0. Okay, so I got two solutions. In this case, we would call that system consistent and independent. I can count to 2, so my system would be independent there. Alright, let's look at the next one. So here, let's solve this one by elimination. So notice that my coefficients are lined up here, so I'm just going to subtract the bottom equation from the top one. Y minus y would equal 0. 4x squared minus a negative x squared would be 5x squared. 8x minus, well, I don't have any linear terms there, so I'm just going to get plus 8x. And I don't have any constant terms up here, so 0 minus a 4 would be negative 4. Okay, so I'm going to try to factor this. I've got 5x and x, 2 and 2, plus and minus. And then I'm going to take and set each one of my factors equal to 0 and try to solve for x. Okay, so x would equal 2/5 and x would equal negative 2. And then once you know what x equals, we need to go back and try to plug into one of our original equations and try to find what y would be. So here y would equal negative 2/5 squared plus 4, which would be negative 4 over 25 plus, rewriting this as a fraction with a denominator of 25. 100 divided by 25 is 4. So I'd end up with 96 over 25 is my y value. So my solution, or one of my solutions, would be the point 2/5, that's my x value, 96 over 25. Doing the same thing over here with the other solution that we got, negative 2. Negative 2 squared is 4, plus 4 is 0, so negative 2, 0 is my other one. So again, we'd call this system consistent and independent. Okay, so just in case the glare there was too much, here's the work that we did there. Plugging stuff in, getting our two solutions, and then describing the system. Okay, so looking at number 3 now, notice that one of our equations in this case is in vertex form, and the other one is in standard form. So in this example here, in order for stuff to be grouped together, we're going to need to multiply out the vertex form and convert it into standard before we can solve. So I'm going to go ahead and write this by doing some substitution just to set up my problem here that I'm doing. I'm setting the two equations equal, and then let's start to multiply this side out. So x minus 2 squared, well, that's x minus 2 times x minus 2. And then distributing there, I'm going to get x squared minus 4x plus 4. Distributing the negative 2 through, plus 8x minus 8 plus 2, And finally, combining like terms, I get negative 2x squared plus 8x minus 6. And I'm setting that equal to, well, what do you know? Negative 2x squared plus 8x minus 6. So when I go to solve this, notice that I'm going to end up eventually with getting 0 equals 0 because both sides are identical. They're both the exact same equation. So what this means is my system is consistent. It has solutions. That's what the consistent part means. And it's also dependent because I can't count the number of solutions. There are infinitely many of them. So this is how you describe the system. But don't get that confused. This is not the same as writing the answer. So the solution to the system would be all the points that are on the equation. So we write that or this is called set builder notation. So it's all the points, x comma y, such that y is equal to, and then really you can pick either one of these equations to write down here since they're both the same one. So y is equal to negative 2x squared plus 8x minus 6. Okay, so the system is consistent and dependent, but the solutions are all the points that are on this equation because these two equations are the same. They're both this one. Okay, and then the last one here, we have two equations that are both written in vertex form. So in that case, I'm probably going to try to graph this to see where they cross at, because vertex form is nice to graph at. What happens with graphing, though, is that sometimes you'll see that they cross and it's not at a whole number solution, which makes graphing almost useless. So graphing was really only a good method if you kind of have a feeling that you're going to get whole number solutions, or it's going to cross at actual points on the graph. So looking at this one, we're going to be shifting it to the left 1 and down 4. 2, 3, 4. That's our vertex. And then our graph opens down, and it's going to be going over 1 and down 2, over 2 and down 8. We'll do the same thing on both sides there. So somewhere down here, we'll call that 8. So the other graph, notice, is going to be shifted also to the left. It's going to the left 3 and up 2. But notice that it opens upward. So it's going to do something like this. And I can tell from the graph here that these two equations aren't going to cross at all. So this system would be called inconsistent, but the answer to the system would be that there is no solution. So there's a big difference between describing the system and writing the actual answer to where these two equations intersect at, or what the answer to the system is. So in this case, the answer is no solution. If you tried to solve this algebraically, what you'd find is that when you're solving it, maybe you get something like negative 2x squared plus 4x plus 17 equals x squared plus 6x plus 11. I just made up these numbers. They're not actually going to be the right ones. However, what you'll find here when you're solving this out is that you either have one or two things happen. Either when you're working it out, you get something like 17 equals negative 3, and that makes no sense whatsoever. So that would be one way you know it has no solution. Or you could also get a quadratic like 2x squared minus 3x minus 7 equals 0. And then when you solve it out and you solve for x, you get things like x equals 3 plus the square root of negative 17. Or 3 plus or minus, because you would get two solutions. So when you get complex numbers, that tells you that it's not going to cross at an actual point also. So those are two ways you can tell algebraically that you're going to get no solution if you didn't choose to graph it and see it that way. So there's different types of ways you can solve this again. You can do substitution. elimination, or sometimes graphing will actually work out, and it'll sometimes be the easiest method, like it is here. If we had wanted to solve this algebraically, we would have had to have multiplied these things out, and that could be a pain. So it just so happened that we got lucky there. So, but just look for little tips to help you. Generally, you're going to solve by either substitution or elimination, just because they're the less risky method, unless the answer or the equations are given to you in vertex form. And then making a quick sketch of the graph can only help you. At least it'll tell you kind of where your equations are. You can also graph most of these things on the calculator and use the function. If you have a TI calculator, you'll press second and then press the trace key up at the top and choose option number 5 where it says intersect, and you'll try to find where the two lines intersect at if you have them both graphed. So that's another good way to check your answer. Sometimes your teacher won't let you use a calculator on the test because it has that function, and they want to see that you've taken the time to learn how to do it algebraically. So anyway, if you have any questions, feel free to leave a comment below. Otherwise, good luck.